Hi there, welcome back to our course on advanced quantum mechanics. This is lecture 24. So we've studied the dynamics of quantum systems. Now, let us ask what happens when, after some dynamics, we perform a measurement. So the new chapter is called Measurement and State Collapse. So let's assume that at some time t, the state is psi, and we measure an observable f. So assume at time t, the state is psi, and we measure a self-adjoint observable f hat. Now, let's assume that our measurement is an ideal measurement. So we ideally measure an observable f hat. Ideally measure a self-adjoint observable f hat. Now here the definition is this. An ideal measurement apparatus, is such that if an outcome of the measurement, let's say Fm, M for measured outcome, is obtained, then if we measure again right away, then an immediate remeasurement, so an infinitesimal amount of time after, an immediate remeasurement will also find the value Fm. And so let's say you measure the energy of a system and you find the value E. Then if it was a good high quality measurement, then if you measure right away again, it should still be the same answer, E. If you measure the position, if it's a high quality measurement, you should find the same position again. Same for momentum and angular momentum and whatnot. So that's what we think of as an ideal measurement. Actually, things are a little bit complicated with observables that have a continuous spectrum, but we will get to that. We will get back to that later. For the moment, let's assume that it's a discrete spectrum, that our observable has a discrete spectrum, such as an angular momentum operator, Hamilton operator, for a harmonic oscillator, and so on. Now there is a consequence of this, corollary. Namely, if an ideal measurement of f hat measures Fm, some value Fm in R, right, is always a real number. then the state of the system becomes a new state. I'm not postulating this. This is a consequence. Becomes a new state. Becomes the state, or becomes, all right, a state, let's call it phi, such that it becomes a state with the property that f bar is equal to phi f hat, phi equal to f m, and delta f squared, which is phi f hat minus f bar squared phi equal to 0. This is not new. This is just rephrasing in mathematical terms what we said up here in words about what an ideal measurement apparatus is. Namely, an ideal measurement apparatus is a measurement apparatus which measures in such a way that what you find, whatever value you find, is reliable in the sense that if you measure right away again, you find the same measurement value. So as a consequence, the state of the system, whatever it was before, we called it psi, after the measurement, the state of the system phi must be such that the expectation value of our observable f is now fm, and there's no spread around it. It must be having variance equal to 0. In other words, by definition, an ideal measurement is such that after the measurement, the state of the system is such that the expected outcome of an immediate measurement now is fm, and there is no uncertainty about it. The usual terminology is we say that the measurement collapsed the state psi in which the system was just before the measurement into the state phi right after the measurement, which has these properties. Now, in a moment, we will calculate what state phi that is. What is that state phi? We can work out what state that is on the basis of knowing its expectation value and its variance. But before that, I would like to make some comments. So, in the form of questions and answers. So, why would one say collapse? Well, it's because in principle, the measurement of the observable f hat could take place as rapidly as you like. It could be very quick. And that means that the change from the state psi just before the measurement to the state phi in which the system is right after the measurement could happen in an arbitrarily short amount of time. And that's why it is said that the state collapses. Well, the answer is, therefore, could be arbitrarily fast. We will have to qualify this statement later when we understand this collapse better. So, you see, an immediate further question then is that what's the physics of this collapse? is the collapse extra? Is it in addition to what we covered in this course before? And the answer is no. Nope. We already covered the collapse. You can't see that just yet, probably, but we have already all the machinery to calculate it. How come? How come we can already calculate the collapse? And why didn't we see it? Well, you see, the collapse seems to be something that is contradicting the dynamics that we have seen so far. The dynamics was governed by the Schrödinger equation, and there was the time-energy uncertainty principle, for example, that showed that things can't happen arbitrarily quickly. The energy has to be tremendously uncertain for something to happen very fast. And also the time evolution is unitary. And this collapse, it appears, might contradict these things. It could be arbitrarily fast. Multiple incoming states could all go into the same outgoing phi state, could collapse. Multiple in states could collapse into the same out state. The same in state could collapse into multiple out states. How can this be unitary? Well, the short answer is that this is not contradicting what we have done so far, because so far we have only covered isolated quantum systems. We have not covered so far how a quantum system interacts with another quantum system. But you see, a measurement process is always the interaction of one quantum system with another one. The measurement apparatus is itself some quantum system. And as we will later see, when we have one quantum system, let's call it quantum system, and we perform a measurement on it, then the natural language to use is to say that, well, yeah, there is a wave function collapse and so on, but we can also understand it with the methods that we have already developed in this course by doing the following. Namely, we can say, consider now the measurement apparatus. So this is the measurement apparatus. And then we can draw a circle or a boundary around both of them. And we can say, this whole thing now, this entire thing consisting of our quantum system and the measurement apparatus can be declared an isolated quantum system, a bigger one, but we had no size limitations on our quantum systems. So we can choose to consider this entire quantum system that consists of the system that we originally considered plus the measurement apparatus. And then we can choose that so big that the whole thing is now isolated. And then we can use the technology that we have already developed in order to study what's going on. In particular, we will see that the measurements that the measurement apparatus is performing on our quantum system are just interactions between these two sub-quantum systems, because measurement apparatuses are also made out of electrons, protons, neutrons, and so on. All of what they are made of, these measurement apparatuses, are also obeying quantum mechanics. So the whole thing is quantum mechanical, and that offers us two ways to look at a measurement. There is the way that we just started our lecture with today, namely to say we have a system and it's being measured. And then we have a wave function collapse. But alternatively, we can also say, wait a moment, the measurement apparatus is quantum mechanical itself. Let's consider the total system consisting of the quantum system and the measurement apparatus. That's a big quantum system, it's isolated, it evolves unitarily, and what is normally viewed as the wave function collapse, the state collapse, is now a dynamical process that takes time. A dynamical process that is governed by the uncertainty principles, by the Schrödinger equation, the Heisenberg equation, unitary time evolution, and the whole thing. We are not quite there yet to be able to do this, but we will just have to study how to describe the interaction between quantum systems, and then we will be ready to do this. But this we will do later, see later. Okay, for now, let's go back to the simple picture where we have a quantum system and it is being measured. And we don't describe the measurement apparatus quantum mechanically, we just describe our system quantum mechanically. So back to the collapse. To the collapse. So we have that the system is in state psi. We measure f hat. We obtain an outcome. And let's call that outcome Fm, some real number. And then, as we discussed above, then the system, so by then I mean right after the measurement, immediately after measurement, the system will be in or collapses into the state. Let's use the language. The system collapses into the state phi, which obeys that, well, the predicted value for f has to be, well, so the expectation value for f has to be Fm, because it's by assumption an ideal measurement. So if we remeasure right away, then we should find the exact same value again and without any uncertainty. So which obeys this, and delta f squared equal to 0. So what is that state phi? What is phi? Well, it's calculated. So what do we know about it? We know that phi has this expectation value, Fm, and we know that its uncertainty is 0. So we have 0, namely the uncertainty is delta f squared, which is what? It is phi f hat minus phi f hat phi, that's the expectation value. And then that's squared, just the usual definition of a variance. Now, by the way, this here, just to remind you, this is f bar. And f bar, the expectation value, is whatever measurement value we found. All right, so what is this? This we can write as phi, and then f hat minus phi f hat phi squared. Oh, wait. I didn't want to square that. I wanted to write this out. So it is this times itself. So times f hat minus phi f hat phi phi. Now, this vector may be called var phi. So therefore, we have that 0 equal to phi phi. This means that the length of the vector phi is 0. And this means that the vector phi itself has to be 0, because in a Hilbert space, the only vector with length 0 is the 0 vector. But what was var phi again? Well, it's this, right? So this must be 0. So therefore, we have that f hat minus phi f hat phi phi equals 0, which is to say that f hat phi equal to, well, what is this again? This is f bar, which is fm. So this is fm phi. So therefore, what we find is phi is the eigenstate of f hat with eigenvalue fm. There's an interesting corollary that follows from this. If f hat is a self-adjoint observable, and we perform an ideal measurement, then the measurement outcomes so that is to say, these numbers fm must be from the spectrum of f hat. Right? So all fm are in the spectrum of f hat. So for example, if, let's say, e.g., harmonic oscillator p hat squared over 2m plus m omega squared half x hat squared, then we have that, and let's say we measured the energy of a harmonic oscillator, then the spectrum of the harmonic oscillator is of course h bar omega 1/2 plus n, where n is element of 0, 1, 2, etc. Then the En are the only possible outcomes. So if you have a harmonic oscillator, let's say in some molecule, when the nuclei vibrate against each other, that's typically harmonic to some good approximation. and you measure the energy levels, then the energy levels are some discrete set of values, and any energy measurement can only ever produce these discrete values. Every individual energy measurement must be from that set of discrete values. And the same is true for any observable with discrete spectrum. The measurement values individually have to be from the spectrum if that observable is a self-adjoint observable. A brief remark, I won't even write it down, is this. If you measure something with a non-ideal measurement, so there is some uncertainty in the reproducibility of the result, but then the collapse will be a bit more complicated, and the formalism that you use in that context is called the POV-M formalism, positive operator valued measures, and we won't have time to get into the details of that. I just wanted to mention that non-ideal measurements can be described. There's a formalism for it, POV-M formalism. Let me just write these keywords. Non-ideal measurement. POV-M formalism. But there's a curiosity, which is that, remember from the time energy uncertainty principle, that if we know the energy of a system completely accurately, then nothing can move in that system. As long as it's isolated, just evolving on its own, then no observable can change its expectation value, right? If we are in an energy eigenstate. So that means that if you perform an ideal measurement of energy, then you're freezing the system. You know what the energy value is, but nothing can happen in that system anymore. No expectation values can change. If you perform a somewhat sloppy measurement of the energy, then the energy uncertainty will be small, but not zero. And then you're slowing down the evolution of the system somewhat. If you perform just a little bit of a measurement of the energy, so that you have some hint of what the energy might be, but with big error bars, then you're just slightly slowing down the system. Now, what I find curious about this is that energy is always measured at least a little bit. And that's because of gravity. And that's because gravity is sensitive to energy, right? Curvature of space-time, the curvature of space-time is sourced by energy. It's just that gravity is a very weak force, so it doesn't measure the energy very much. But in principle, it's curious to know that gravity is measuring energy and therefore is sort of trying to slow quantum evolutions down. It's just that gravity is such a weak force in normal circumstances that the effect is negligible. But who knows? Maybe there are some circumstances where it's important. Okay, so what do we have so far? So far, we have that ideal measurements lead to collapse into an eigenstate of the observable that we measure. Now, but this leads to the question, with what probability will this happen? So if the system is in state psi, what is the probability for a collapse into the state phi? Well, in a measurement, in a measurement. Okay, just in a measurement, let's say. Now, you may wonder, we didn't cover that so far. We covered in this course, we uncovered in this course that the outcomes of quantum mechanical measurements cannot be predicted with certainty usually, and that there is going to be an expectation value for each observable and that there's going to be some variance around that expectation value. But we didn't actually calculate a single probability so far. And you may wonder, is that now the time to introduce a new axiom that tells us how probabilities are to be calculated? And the answer is no. We already know how to calculate probabilities. We just didn't do it. Let me show you. It's already in our formalism. We can do it. So for the answer, we have to consider a special kind of observable. Namely, consider the observable Qhat, which we define to be phi phi. Is it self-adjoint? Yes. You see, Qhat dagger is what? Well, it's this again, right? Because if you apply the dagger to this, this bra becomes a cat and this cat becomes a bra. Yes, it is definitely a self-adjoint operator, and it's an observable. Now, the outcomes are what? Possible measurement outcomes. Well, let's call them little q. Possible measurement outcomes q are what? Well, we know that the q must be from the spectrum of our operator Qhat. So what is the spectrum of Qhat? That will tell us what the measurement outcome is, what the range of possible measurement outcomes is. Well, we start by notice that Qhat squared is equal to phi, 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 phi. But that's just the length of the vectors. That's just one, because all our state vectors are normalized. So this, therefore, is phi, phi, also known as Qhat. So what we have is, so Qhat dagger is Qhat, and Qhat squared is equal to Qhat. Therefore, Qhat is a projector. All right, so we have an observable here, which is a projector. Then I think we covered before what the possible eigenvalues of a projector are, but let's just look at it again. So assume, because it's so important, assume that Q hat acting on one of its eigenstates is Q. So these are the eigenstates and these are the eigenvalues. Well then, we have that Q is equal to Q hat Q, which is equal to Q hat squared Q, which is what? Well, it is Q squared Q. So therefore, we have that Q is equal to Q squared, and therefore we have that Q must be an element of the set which contains two values, 0 and 1. Because only 0 obeys 0 equals 0 squared, and 1 obeys 1 equals 1 squared. No other number obeys that condition here. So what we have is, so the spectrum of our Q hat operator is actually the set of values 0 and 1. So if we find, if we can design a measurement apparatus that measures Q hat, well, it will have two possible outcomes, 0 and 1. Now, what are the eigenvectors corresponding to 0 and to 1? Eigenvectors. Well, eigenvector to eigenvalue 1 is phi, as you may already have suspected. Namely, if we calculate what is Q hat acting on phi, well, this is phi, because that's what Q hat is, acting on phi. This being 1, it is phi. So yes, phi hat is eigenvector to Q hat with eigenvalue 1. That's the eigenvector to eigenvalue 1. And then any state alpha which is orthogonal to phi is eigenvector to eigenvalue 0. Namely, Q hat acting on alpha equal to phi alpha equal to 0. Right? Because by assumption, phi and alpha are orthogonal to each other. All right, so what we found is the spectrum of Q hat and its eigenvectors. Namely, phi is eigenvector to eigenvalue 1, and all the others, and the orthogonal complement of the Hilbert space consists of eigenvectors with eigenvalue 0. So now, let's imagine we measure our observable Q hat. Let me say something more about the significance of observables of that type. A projector is an elementary observable in the sense that it has only two different eigenvalues, in this case 0 or 1, and therefore the amount of information that you gain when you perform a measurement of Q hat is only what is contained in a 0 or 1. So you can only get almost 1 bit of information out of this. And you can't have less information than that. So it's, in a sense, the most elementary measurement that you can do. Okay, so now imagine we actually perform an ensemble of measurements of Q hat. So we run the same experiment many times, and then at the same experiment time t, we perform the measurement Q. And in some of the runs of the experiment, we will find the value 1, and in some runs of the experiment, we will find the value 0. So assume we do an ensemble measurement of Q hat. So we run the same experiment from the same initial condition multiple times. At the same time, experiment time, we perform the measurement of Q hat. We get lots of outcomes. Some of them will be 1s, some of them will be 0s. And in particular, we get value 1 when phi is found in the measurement, and then we get value 0 else. The experiment only gives us the information whether or not we find the state phi. And this means that, and this is now super important, this means that the mean value of Q, the expected value of Q is, first of all, the proportion of cases where phi was found, right? Because all those experimental runs where we did find phi produced a 1. All those experimental runs where we didn't find phi produced a 0. So if we take the average of all those 1s and all those 0s, we get a number between 0 and 1. In the interval from 0 to 1, we get a number from 0 to 1, and it is the proportion of positive findings of phi. In other words, this is the probability. So this is the probability for finding phi in the measurement. So let us summarize that, because it's a super important point here. So therefore, if a system is prepared, it might have evolved into that state. So is in a state psi at time t, and we look for the state phi, namely by measuring the observable Q hat, then the probability for finding it is, well, let me write it in red, is probability for phi equal to the expectation value of Q, which is psi Q hat psi. But what is that? That is psi, and then Q hat is phi phi. right? And then psi. And this is, well, it is phi psi modulus squared. So we obtained here the so-called Born rule. And the Born rule says that if system is in state psi, then the probability to measure phi is, well, this expression above. It's this overlap here of phi psi modulus squared. And that is indeed always a number which is between 0 and 1, as a probability should be, right? Because both are normalized vectors, so this overlap is the length of phi times the length of psi, both being 1, times the cosine of the angle between the two. So the probability for finding phi is maximal if we choose phi to be psi, then it's just 1. But if we choose any other state, then, well, what we are finding here is that the probability is the square of the overlap. So how much of phi is in psi in the linear algebra sense? If we linearly combine psi as phi and states orthogonal to phi, it's the component that is parallel to psi, which is determining how likely it is to find phi when psi is the state of the system. This number in here is called the probability amplitude. Probability amplitude. And it plays a huge role in Feynman's approach to quantum mechanics that we will get to towards the end of the course when we will cover the Feynman path integral. So, for example, then, let's say system is in state psi at t, then what is the probability to find energy eigenstate En then? If we measure the energy, of course, well, then the probability of finding En is obviously En psi squared. But on the other hand, what is the probability density? I will explain in a moment why density. Probability density to find position x. Well, by the same principle, by the same Born rule, we find that the probability density for finding, well, actually, I shouldn't say the state because we never measure vectors, we measure eigenvalues. So the probability for finding a particular position x is then, by the Born rule again, x psi squared. Now it's not a probability, it's a probability density, because the x is not a normalizable vector and it's part of the continuous spectrum. And remember that then we need to integrate. This was this business with the Stiltius integral. We need to integrate in order to get a finite value. So in particular, what we have is that the probability, an actual probability, not the probability density, so the probability to find, or for finding, I should say, probability for finding a position between or in the interval xa to xb is, so probability for finding xa to xb, this is then the integral from xa to xb x psi squared dx. And of course, you know this as the integral over the modulus squared of the position wave function. Now, where does this come from? How can you derive this? I'm just stating it here, but how to derive the letter? How to derive this? So let's call this star. Well, question, answer, use the observable, a projector. Let me just say words. Use the observable Qhat, which is the integral from xa to xb of x dx. If you use this observable and you run through the same arguments that we went through in this lecture, then you find that you get this Born rule when you're asking for the probability that the particle will be found inside a certain interval. And notice that, x is not a projector because, well, let's see what happens when we square it. See, this is equal to the Dirac delta of x minus x equal to the Dirac delta of 0, which is not defined, or infinite if you like. But Qhat is a projector. We have Qhat squared is equal to Qhat, and we also have that Qhat dagger is Qhat. It is worth checking this, especially this one. Check it out yourself that this is true. It's quite important. Okay, so what we've seen is that the probability interpretation of quantum mechanics was already built in. And the reason is that once we know how to predict expectation values, we know how to calculate probabilities. And the reason is that among the set of all observables, are projectors. Projectors are observables. And these projectors have only two eigenvalues, 0 and 1. And their expectation values are therefore probabilities. So the probabilities popped up. All right, so this is as far as we got today. See you then.